Hi everybody, welcome back. If you've been following along, we're moving on to episode number 7, and hello everybody if you're just jumping in and starting right now. For those of you who haven't been here, or even a reminder for those of you who have been following along, I'm doing a series of lectures that follow the BC Chemistry 12 curriculum to hopefully cover us from the time we were out of school and through the late spring, early summer, to get us through the COVID-19 pandemic, where we're all staying at home. So today's episode was going to be a series of, I was going to look at a whole bunch of different scenarios, calculation types of questions regarding acids. What I decided to do is I'm going to do shorter 6 in a row little ones. Rather than have all of them on one video, I think it might be a little bit too long then. You may not need to see all of the examples that I do. You might only want to kind of pick and choose. So I'm going to separate them. They'll be much shorter, kind of cut to the chase, and I'll put them all up. They'll all be episode 7, but I'm going to label them A, B, C, D, E, and F. And you'll see the title, so you'll be able to tell kind of what it is that I'm trying to do. So the first one that I want to do is, you can kind of see up here on the board. It's calculating the Ka of a weak acid. So when would you want to calculate the Ka of a weak acid? Well, oftentimes, as we've seen in the past, when you've got your Ka table, you know what the Ka is of a weak acid. But a couple of things. Number one, you only know this value at 25 degrees. Well, what if you're experimenting and you're not at 25 degrees and you want to find out the Ka at a different temperature? What if the acid that you've got an acid because it's got an acidic pH, but you don't know what the acid is? One of the identifying features of an acid is its Ka at 25 degrees. If you could solve that mathematically and then compare it to a table with known values, you'd be able to identify what that acid would be. So there are a lot of experimental techniques that we're going to get into later on. When we do the titration unit is about the experimental means by which you can figure out all these things for an acid. And from the information that you gather from a titration, you can do some of these things that I'm about to do in the next few videos about scenarios for acid calculations. This is one of them. So you would collect experimental data from a titration, and that would allow you to calculate the Ka. So if you had an unknown acid, you could do a titration, not even knowing what the acid is. You can still do the titration. You can gather the experimental data, and you can use that data to calculate the Ka of the unknown, and then perhaps identify what it is. So this is the first one for today, is calculating the Ka. You can see that the next one is going to have to do with initial concentrations given information, and you're trying to calculate. It's kind of going backwards from a pH to a concentration. So today, Ka. So I'm going to put a question up on the board, and this is how all 6 of these are going to look. I'll start with a question. We'll just go through that question, and then it's hopefully general enough that you'll be able to take the general principles that we talk about and be able to apply them to any similar scenario. So the question that I'm going to give you here. So we have, and you have to remember that this is connected to an experimental, probably titration. So once you do a titration, you would be doing an experiment. We're not going to be probably in class to be able to do these things, but later in your chemistry future, this is the type of thing that you might do. So here's the question. An unknown weak monoprotic acid HX has an initial initial concentration of 0.722 molar. Okay, so that would be determined through a titration, which is way more complicated than me just putting up the number. Okay, so when we get to titration, that will be one of the critical things, is what's the initial concentration of the acid in the very first place. Titration tells you that. So there's our initial concentration of that acid, and a pH equal to 3.59. What is its Ka? So we know the initial, we know the pH. Okay, so that's all we know. We know it's in acid, and it says it's weak, which means it forms an equilibrium. It doesn't go 100%. It says it's monoprotic. Monoprotic, mono means one, proton, protic. So it's got one hydrogen to donate. We will eventually get to polyprotic species where they have 2 H's or 3 H's, and they have the ability to donate more than one. Monoprotic means it only has one to donate, and once it gets rid of that, it's done. A diprotic acid will have an H, and then it's got another one to donate as well, which complicates the issue. Certainly during titration, it complicates the issue. So it's an important descriptor of being monoprotic. So monoprotic acid in water has a pH of 3.59. So first thing I'm going to do is I'm going to write down a generic equilibrium equation for this, and then an IRE table. I'm going to write it a little bit small because I'm going to need quite a bit of room here on the board. So okay, so there's my equilibrium. HX is aqueous, water is liquid, produces hydronium, and X minus, whatever X minus is. And then your initial, your reaction, and your equilibrium. Don't panic that I have an R and other people might have a C. It doesn't mean I'm right or wrong, and your teacher's right or wrong. It doesn't matter. It's just that semantics. It doesn't really matter. So that middle line is the changes that go on during the reaction. So what do we know? Well, clearly we know the initial concentration, the titration that would have been in the history of this question is told to us. (0.722). We also know the initial concentration of the hydronium and the X minus. I'm going to cross out water because water is a liquid. And liquids don't change concentration, so I'm not going to put that one in. Recall from the last class that I was doing weak acids, or talking about weak acids, the hydronium concentration starts in distilled water as 1 times 10 to the negative 7, which is essentially, for all intents and purposes, 0. And that's why we start with a 0 there. Okay, now what else do we know? The other thing that is given to us is pH. Well, where does the pH fit into this IRE table? A, what chemical is it referring to? And B, what time frame is it referring to? So pH is referring to the hydronium and only the hydronium. pH has nothing to, pH is not connected mathematically to the HX concentration. pH is a measure of hydronium. And you have to remember that. So anytime you're given a pH, it's like you're being given the hydronium concentration. So this pH right here, that 3.59, is given so that we can figure out the hydronium. So you have to go back and say to yourself, well, how do you get the hydronium from a pH? Hydronium concentration equals 10 to the power of that negative hydronium. Sorry, the screen went dark on me there. So 10 to the power of the negative pH is going to be whatever the hydronium is. So I'm going to grab my calculator. The hydronium is going to be 10 to the power of negative 3.59. So on my calculator, grab my glasses as well. 10 to the power of negative 3.59. And I get 2.57 times 10 to the negative 4. How many sig figs do I get? The pH, the number before the decimal doesn't count, the numbers after the decimal do count. So only the 5 and the 9 are significant, the 3 is not. So it has 2 sig figs. So my answer comes out to, I round it to 2.6 times 10 to the negative 4. Let me write that a little bit more clear because I'm not sure you'll be able to see that from where you're sitting. So 2.6 times 10 to the negative 4 molar. Now, where is that number going? Like, where is that? Is that like initial? You might think it's initial because you're like, if you've got a beaker with the acid in it and you put the pH meter in, isn't that initial? It's actually not. If you've taken the pH of a solution, you're taking the pH of the solution after it's already done its thing and it's sitting there at equilibrium. Remember, this solution was made way back when in the history of this solution by taking water, taking HX, mixing them together, dissolving it. It did its equilibrium thing, like it got to equilibrium, and then it's sitting there on the countertop. And then you go and get it, and you do whatever you're going to do to it. You grab your pH meter and stick it in. It's already at equilibrium. You have to kind of get that chronology of events, that a solution sitting there is sitting there at equilibrium. Okay? Which means that when you measure this pH, and from the pH you get the hydronium concentration, that's my equilibrium hydronium. So that goes here. And because the hydronium went from 0 up to that number, that means this went up 2.6 times 10 to the negative 4. This went down. Sorry, this also went up 2.6 times 10 to the negative 4. Okay, so both of those values on the E line are 2.6 times 10 to the negative 4. This one went down 2.6 times 10 to the negative 4. So I'm actually going to do that subtraction. Now, it may or may not change it using subtraction Sig Fig rules. We'll see in just a little second here, but you have to recognize that if one side goes up in concentration, the other side of the reaction has to go down, whichever way it's going. So initially 7.722 of the acid reacted to produce some of that hydronium. The pH is telling you how much hydronium it actually made. So now let's do that subtraction. And to be able to tell if that subtraction should have, like using your Sig Fig rules, if actually it's going to change the value, I'm going to make it visual. So I'm going to put it up here on the board just so that you can see it, which is going to require me to take 2.6 times 10 to the negative 4 out of scientific notation so you can kind of see the place value. 0, 0, 0, 2, 6. So this one down here, that is 2.6 times 10 to the negative 4. Now when I do this subtraction and I get 0.72174. Okay, so like if you do it on your calculator, that's what you're going to get. Your calculator will give you that value. Now I'm supposed to know where I'm rounding that off. And so since 0.722 has 3 decimal places, or 3 place values, this one has 5. I'm only allowed 3 place values on the subtraction, so I have to round it off right there. And when you round it off, it's 0.72. It either stays as a 1 or rounds up to a 2. Well, because there's a 7 right there, it rounds up to a 2, which means that you're just back to 0.722. So in fact, it didn't actually have any effect when you take significant figures into account. So it is that value that was subtracted is insignificant relative to the level of precision of 0.722. Okay, so which is kind of the purpose of sig figs in the very first place. So now we've got numbers along the E line. So in the calculations we did last class in episode 6, we had variables there, but we knew the Ka. This time we don't know the Ka, we have values for our equilibrium. So now we need an equilibrium expression, plug in our values, and boom, do the calculation, there's our Ka. So let's write down the K expression. Products, hydronium, times whatever X minus is, remember we don't know what it is, over the concentration of HX. And we're taking the equilibrium numbers. Now, I want you to pay really close attention to which value you're taking, because in this example I'm giving you, this guy right here didn't change, but oftentimes it does change. Like you'll start with 0.722, and that number that you're subtracting actually does have a significant effect. So don't just ignore it. Don't pretend it doesn't happen, because it can happen. So make sure you actually follow through with the subtraction, check the sig figs, and use the subtraction rule and see if it actually changed. Then you're using the equilibrium numbers, right? You're using the IRE table to find out what those numbers are. Everything in the I and the R line doesn't matter anymore. Once you've got numbers on the E line, doesn't matter anymore. So then I plug in my values and I use my calculator and I figure out what Ka is. So let's plug it in. And I've got 2.6 times 10 to the negative 4 times 2.6 times 10 to the negative 4, or just squared if you want, that's fine, divided by 0.722. Well, that's going to come out to 2 sig figs. Now, just a little bit of a sig fig rule here, because what I've done is what I encourage you not to do from a sig fig perspective. So what I've done is I've taken this and I've rounded it to 2 sig figs. I've put it in here with 2 sig figs. I've put it into here with 2 sig figs. But if I do the calculation now and then I round again to 2 sig figs, I've double rounded. I rounded the first time and then I rounded the second time. In reality, this 2.6 right here, I don't know if you remember what the number was, but it was 2.57 something, 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 something times 10 to the negative 4. Why wouldn't I just keep doing that? Because I technically, instead of putting 2.6 times 10 to the negative 4 here, I could have put 10 to the power of negative 3.59. Done the math, divided by 0.722, and then rounded at the very end once, which is what you should technically do. Which means what I'm going to do is I'm going to go back to my calculator, and this is my tendency, like I've still got it. Can you see on there? Sure you can see on there. I've still got that original number. I didn't even erase it. It's still sitting there. It's 2.57039578 times 10 to the negative 4. It's still there. So now I'm going to use that instead of 2.6 times 10 to the negative 4. So now I'm going to square that value. Okay, here we are. Then I'm going to divide by 0.722, and I get, now it may not make a speck of difference, right? Like I might have gone through all of that for no reason. 2.6 times 10 to the negative 4 times 2.6 times 10 to the negative 4. Maybe it gives you the exact same answer once you round it to 2 sig figs. Maybe, maybe not. I don't know. But the proper way of doing it is to not round too many times. Round when you have to round, meaning switching Sig Fig rules, or wait to the very end. So if everything's just multiplication, exponents, division, you should be rounding once, and that's at the very, very end. So I get the whole long answer is 9.150878 times 10 to the negative 8. Oh, it did it to me again. So that's what the value is with the long thing. Now I'm going to round, so 9.15. That 5 makes the 1 round up to a 2. So I get 9.2 times 10 to the negative 8. Okay, so the idea with a Ka is you have to know the initial concentration of the acid, which is what titrations will do for you as you see experimentally. And then you have to have a pH to give you some information about the E line. And then once you've got numbers in there, K expression, plug them in, you're good to go. Now, if someone asked me, identify the acid, right? So instead of what's the Ka, but someone said, identify the acid, this would be an identifying feature. So I could now go to a table, as long as it was at the right temperature, that the table and what the experiment was being done at, I can now compare. And I could look for a weak monoprotic acid on the table, given the formula, and I could look for 9.2 times 10 to the negative 8 and see which one it matched up with, and that would most likely be my acid. Okay, great. We'll see you next time, and in the next one, we are determining the initial concentration of a weak acid.